Let's now talk about the application of integration to kinematics. As you've seen, if we have a position versus time graph, here's a particle that goes to some positive distance, stops, and turns around and comes back to the origin. Well, how can we relate that to velocity? If you take the derivative of position with respect to time, you get velocity. ds dt is velocity. So now we have a velocity time graph. Well, what's happening here? Positive derivative, 0. So we have positive derivative, 0. And then we have negative derivative, negative derivative, negative derivative. What's the derivative of this? Well, dv dt is acceleration, or how fast is velocity changing. Look at, we have a constant slope here, and it's constantly negative, so our acceleration is constantly negative there. Negative second derivative means concave down. It makes sense. Well, how do we get from acceleration back to velocity? The integral of acceleration with respect to time is velocity. How do we get back from velocity to displacement? Well, the integral of velocity with respect to time is displacement. Going down in the levels, you take the derivative, which is the slope of the tangent at a certain point. Going up levels, we take the area under the curve, and that is how we get from acceleration back to velocity, velocity back to position or displacement. Only a cautionary tale here. Careful with your terminology. Displacement is associated with net distance. If I run out there 100 yards and I run back 99, my displacement is only 1 yard. But my total distance would be out 99 and out 100 and back 99 for a total distance of 199. Well, how does that play in? We saw it play into our integration graphs. We saw in our last slide that if we had velocity and time and we integrated, we get position versus time, or displacement versus time. So if I have, here's velocity and here is time. In other words, I could call this ds dt. I've taken the derivative. I want to get back to displacement. Well, this is where the signed area versus splitting up the areas comes into effect. If I want to talk displacement, then all I have to do is from t1 to t2, I integrate from t1 to t2 of v dt, my velocity with respect to time. If I want to find the total distance, then this is what we call the signed area here. That's the signed area. Well, if I want to find distance, I have to split it up. From here is the point A. I have to integrate from t1 to A of v dt plus from A to t2 of v dt. What am I missing? Well, our area here is below the x-axis, so I'd have to take the opposite of that to make this a positive value plus another positive value, and that's associated with the total distance. Here's an example of what we were just talking about, using displacement versus distance and the signed area. The velocity of an object, so we're talking kinematics, is v meters per second after t seconds, where our relationship is velocity equals 1 minus 2 sine 2t. So we're given the velocity versus time graph. We know if we integrate that, we're going to get displacement. Find the object's displacement. So I'm thinking displacement is signed area. I'm only concerned with the signed area over the first 3 pi over 4 seconds. So I just have to integrate from 0 to 3 pi over 4. Integrate what? 1 minus 2 sine 2t with respect to t. So please don't forget that dt. Well, that means I just have to integrate this. 1 t to the 0 becomes t minus, well, our 2 is a constant. Sine goes to negative cosine of what? Of 2t divided by 2, or times 1/2. And I'm going to integrate this from 0 to 3 pi over 4. Well, I can simplify this. The 2's will cancel and the negative will cancel into a positive. So I'm left with t plus cosine 2t from 0 to 3 pi over 4. I'm going to plug those in, which is 3 pi over 4 plus cosine 2 times 3 pi over 4 minus, if I plug in the 0 here, I have 0 plus cosine 2 times 0 is 0, which ultimately will give me, when I work this all out, 3 pi over 4 minus 1, which is equal to 1.36. I use 3 significant figures, and meters is my unit. So that is my displacement. That's the signed area. Now the second part of this problem says the velocity of an object, v meters per second, after t seconds, where v is equal to 1 minus 2 sine 2t. The second part of this problem says find the distance traveled. So now we're talking about total area. No longer just the signed area. So we're going to have to break our problem down into different parts based on if our graph is above or below the x-axis. Well, how do we know? Well, first we need to know, I've got a sketch here already. Maybe you find this on your graphing calculator, or maybe you remember your trig, which we're going to be going over later, and produce this graph. It's not too hard. You have to see that, well, we have two x-intercepts. So we have to know our stop and end points for integration. Well, how do we find x-intercepts? Set your function 1 minus 2 sine 2t equal to 0. Set y equal to 0 to find x-intercepts. Well, I can subtract 1 from both sides, and I get negative 2 sine 2t equals negative 1. I can now divide both sides by the negative 2, and I get sine 2t equals 1/2. So 2t equals arc sine 1/2. Well, again, we're going to have to work on our trig if you don't know how to do that. Ultimately, you're asking yourself, where does sine equal 1/2? Well, it's a cyclical function. That's pi over 6 and 5 pi over 6. If you don't know that, well, we'll talk about that in our trig section. Now I can divide each of these by 2, and I'm getting t is equal to pi over 12, comma, 5 pi over 12. These, of course, we're going to have more x-intercepts, but I just found the two I'm looking for, pi over 12 and 5 pi over 12. Why do I need those? Because I need to know where to integrate. Now that we know our x-intercepts are pi over 12 and 5 pi over 12, we can integrate this. I'm trying to find the total distance, so I want 0 to pi over 12 of my function. 1 minus 2 sine 2t dt plus, well, from pi over 12 to 5 pi over 12, I've got a curve that's below the x-axis. So I'm going to take the opposite of that from pi over 12 to 5 pi over 12 of my function, again, is 1 minus 2 sine 2t, again, with respect to t. And last but not least, I'm going to add from 5 pi over 12, add from 5 pi over 12 to 3 pi over 4. That's our endpoint there. 3 pi over 4. It was given to us from 0 to 3 pi over 4. That was given to us in the problem. Of, again, my function is 1 minus 2 sine 2t with respect to dt. If you integrate this, take the opposite of the middle part, which is under the curve of the under the x-axis, and then add it to this last part here. Ultimately, 3 sig figs, you get 2.73 what? Meters. Because we're looking for distance traveled. We had velocity, we integrate, and we get distance traveled when we take total area.